So today we're going to see transformers in action. So what I have here is the primary coil of a transformer. That means it's the coil that's connected to the power supply. In this case, this is a 220 turn coil, which is connected to an ordinary wall outlet, 110 volts AC. So when I close the switch, which I'll do in a little bit, I'm going to be driving an alternating current, which is alternating back and forth 60 times per second, 110 volts, just like you get from any wall outlet in your house. And this is my secondary, and what you see is that this coil is not connected to any wall outlet. It's freestanding, but I put this coil over the primary. So now when the primary has an oscillating current in it, making an oscillating magnetic field, according to Faraday's law, that oscillating magnetic field will induce a current in the secondary. But because the secondary is 10,000 turns and the primary is 220 turns, in the secondary, I'm not going to have just 110 volts. I'm going to have 5,000 volts. Actually, in fact, I'll have more than 5,000 volts because if you look at this carefully, this primary is 220 turns, but not all of those turns are inside the secondary. So the effective number of turns is actually less than 220. And so the ratio of voltages is going to be more than the ratio of 10,000 to 220. So actually, I'm going to have more than 5,000 volts in this coil. And let's see what happens. Here we go. Look at that. So when I close the switch, I have a 110 volt oscillating current in the primary and more than 5,000 volt oscillating current in the secondary. And that voltage in the secondary is high enough to drive a spark between these two wires. So the secondary, one side of the coil is connected to this side, one side is connected to that side, and there's a gap there, a gap with air in it. And, but the voltage, 110 volts cannot drive a spark across, that looks like about 3/4 of a centimeter there. There's no way 110 volts can make a spark there, but the voltage in the secondary is enough to make a spark, and you see it. There's the spark, there's the spark, and there's the spark. And that's the transformer story, but it's also fun to ask why this spark, why this discharge rises like this. This setup is called Jacob's ladder, and how does it work? Well, when I close the switch, a spark jumps across here. What does that mean? It means that current is flowing through the air, and that current is ripping electrons off the air molecules, making a discharge, making a glowing, very white-hot line of plasma, which is the spark, a little mini bolt of lightning, and hot gas rises. So that heated, that line of heated gas starts to rise, and then instead of making a new spark at the bottom, it's the easiest place for the circuit to close is to use the existing little lightning bolt, and since that lightning bolt has risen, what you see is the Jacob's ladder phenomenon where the spark rises. So let's watch it again. And then, once the spark gets up to here, the heated gas keeps rising, but it's beyond the tips of the wires, so no current is flowing up here anymore, and then a new spark jumps down at the bottom and it starts over again. So let's watch again. The spark rises, breaks, and then a new one starts. Rises, breaks, and a new one starts. Okay. Now, there's an easy way to test whether what I told you is correct. If I do the following, let me start it, and then I'm going to blow it out. So what's happening when I blow it out is that the spark, that hot plasma was rising, and then because I was exhaling, I was blowing a breath of air, the air was moving this way. So that hot gas gets blown that way, and it's no longer between the wires. So this spark stops, and then a new one starts at the bottom with a brand new spark, which starts rising again, and then I blew it out again. So that's a transformer set up so as to be a step-up transformer, because you take the 110 volts here and you step it up to over 5,000 volts in the secondary. So, and we used those 5,000 volts to drive the Jacob's ladder phenomenon, which was kind of fun. And what we're going to do next is I'm going to put a new coil, a new secondary, which instead of having 10,000 turns is going to have just one turn. So let's do that next. If you look and see what we have here, this is a band of copper. It's a rather wide band of copper. Why do we have that set up? Well, if I have a 220 turn primary and a 1 turn secondary, that means in the secondary the voltage is going to be pretty low, but the current is going to be enormous. Because I drop the voltage by a factor of maybe 200, but I increase the current by that same factor. So I'm going to be driving a large current through this single turn coil, through this band of copper. And the way we've set this up is that this band of copper, instead of being interrupted by an air gap like before when we did the Jacob's ladder, it's interrupted by an iron nail. There's an old iron nail connected across the gap in this copper. So I want to make sure that I've explained this well, because once we do this, I'm not going to put my fingers anywhere near it. So I'm going to close the switch. This time I'm actually going to drive 208 volts. When I close the switch this way, I'm connected to a power supply like the one that might power your electric dryer at home. I'm going to drive 208 volts through the primary. The secondary has 1/200th of that in voltage, but it's going to have 200 times the current. And we'll see what that current does. When you drive a very large current through this nail, let's see what happens. Here we go. So there's a current flowing through the nail. I can smell what's happening. I can see what's happening. It's going red hot. It's going red hot. It's smoking, and there, it just broke. So I just melted that nail. It went red hot, then white hot, and then it broke. That's what happens when you drive so much current through a nail. And now you see why I needed to have such a wide band of copper. I didn't want the copper to melt. I only wanted the nail to melt. And that's how you use a transformer to melt a nail.